In this video, we will begin looking at growth models, in particular linear growth models. Those are growth models that are in the shape of a line. And we're going to look at two different types of formats for our equations, both recursive and explicit. So let's talk about what those are. A recursive relationship is a formula which relates the next value in a sequence to the previous value. So if you have some value here, right, and you want to get to the next value, then you understand what happens to get there. Like you understand this rule. Perhaps it's like you add, 5, for example, to get to the next term. This is an excellent way to describe how a quantity is changing, but it's not convenient for making predictions that stretch far into the future because you would have to continue doing the next and then the next and so on. So the second version is an explicit equation that allows us to calculate a value in a sequence directly without needing to know the previous terms. In other words, if we want to know some, like let's say we're here, in our sequence, and there's a whole bunch of sequence terms, and we want to jump somewhere way into the future, way over here, we can do that with an explicit equation that takes us directly there. We don't have to know what's in between those two. So let's take a look at some examples because that's very vague what I'm saying. All right, here's an example of two different sequences. We'll talk a little bit about both. Let's examine them. Okay, let's take a look at the one on the left, 7, 15, 23, 31, 39. Now this is a linear growth because what happens is to get from 7 to 15, you can just simply add 8. 7 plus 8 is 15. And then once again, you can add 8 to 15 and get 23. 23 plus 8 would give you 31. And 31 plus 8 would give you 39. And so we could actually talk about the next term, even though we don't see it, by just adding 8 each time. That would take us to 47 and so on. All right. Understanding that adding 8 each time is recursive. That's the recursive idea. We add 8 to get to the next term. Okay, now that's well and fine unless I want to go way, way, way out there and I ask something like, okay, well, what is the 50th term? Well, I'd have to keep going. Okay, first term, second term, third term, fourth term, fifth term, sixth term. I have to go all the way to the 50th term. And that might be a bit tedious. Okay, explicit would be more like recognizing what's going on as a means of computation. So we would say something like, well, the first term is 7, right? And the next term really is 7 plus 8 more, right? That's 15. Notice I'm writing it as 7 plus 8. The next term is 23. That's adding another 8. So I would say like it's 7 plus 8 plus another 8. That's 23. And then 7 plus 8 plus 8 plus 8. Now you may be thinking like, ooh, that looks worse. I'm writing it worse. Well, when you write it like this, you might be able to recognize some features about it. Is that the first term is 7. The second term is 7 plus, 8 once. That's the second term. The third term, right, is 7 plus 8 twice. And then the fourth term is 7 plus 8 3 times. So it's a different way to recognize that, oh, okay, really all that I have is all of these terms are 7 plus some number of 8s. And you can use that to think about the term way out into the future, if you can find that relationship. Okay, now let's take a look at the second example to the right. It also is linear. This time it's not adding. Well, it is adding if you want to think of adding a negative. But I like to think of it in terms of subtraction, right? 7. If you take away 4.5 or 4.5, you get to 2.5. Now I'm going to grab my calculator because I'm going to keep going with this notion right here, right? If we subtract another 4.5, we get down to -2. Okay, if we subtract another -4.5 or subtract another 4.5, we get to -6.5. And we could continue doing that just by subtracting 4.5. And the next one would be, let's see, -11, right? -11 would be our next term. And so on. Okay. So recursively, what we can do to find the next term is keep subtracting 4.5. Now, that's a great way to understand it because you can see there I'm subtracting 4.5. However, it's not great at predicting the future. So I would like to think about, okay, explicitly what's going on. Well, explicitly what's going on is I started at 7, just like the other sequence, right? But each time I get to the next term, I subtract a 4.5. So I would say like, well, the first term is 7. The next term is 7, take away a 4.5, right? The next term is 7, take away 2 4.5. So 4.5 times 2. The next one would be 7, take away 4.5 times 3, and so on. That's more explicit to think about. So that any term could be found by subtracting some number of 4.5s. Now let's get a little more specific about this, and let's take a look at some examples, and then a formula that I'll show you. So here's an example. The city of Cleansburg is considering a new law that would restrict the monthly amount of garbage allowed to be dumped in the local landfill to a maximum of 120 tons per month. There's a concern among local officials that unless this restriction on dumping is imposed, the landfill will reach its maximum capacity of 20,000 tons. That's as big as the dump can get in a few years. Currently, there are 8,000 tons of garbage already in the landfill. So assume that the law is passed and the landfill collects exactly 120 tons of garbage each month. How much garbage will there be in the landfill 5 years from now? How long before the landfill reaches its 20,000 ton capacity? That's the concern. So you can do this explicitly or you can do it recursively. And I'm going to show you these formulas down here in just a second. But let's actually reason this out a little bit first. Okay, so really what's going on is we are starting off with 8,000 tons of garbage, right, in the dump. That's what it says right here in the middle of it, right? And each month we're going to be adding another 120. So if the next month you would say, okay, we'd have 8,000 plus another 120. And then the next month you add another 120, takes you to 8,240. And the next month you add another 120, 8,360, and so on, right? You can kind of see that that's how that's working out. So recursively, you're just adding 120. Now, that would take us a while to do the first 5 years, because 5 years, let's make a little note of this here, right? 5 years is equal to 12 times 5, 60 months. Okay. So I would have to do this, move 60 times, 1, 2, 3, and I might get a little tired of that. So explicitly, I might do this a little easier by saying, okay, start with 8,000, then I'll have 8,000 plus 120, right? One time, and then I'll have 8,000 plus 120 2 times. That's this term right here, and then I'll have 8,000 plus 120 3 times, and so on. I did a little extra parenthesis there. But the idea would be like you just start with the 8,000 and you add in some number of 120s. Well, how many 120s? Well, we're going to talk about 5 years, so that's 60 months. So really, way out in the future, what we want 5 years later, right? 5 years later would be the 8,000 we started with plus 120 tons times the 60 months. Now, that's something we can just compute right onto our calculator. In fact, I'll do that right now. Now, remember the order of operations to do 120 times 60 first would be 8,000 plus 7,200 or 15,200. So it turns out 5 years later, we're still okay as far as we haven't gone over the 20,000 tons. But you can see that we are getting fairly close. And so the question then says, well, how long before it reaches the 20,000 ton capacity? That might be something we would want an equation for. Now, I took the liberty of taking from the author a graph. You can see that a graph, if we were to plot these points, 8,000, 8,120, 8,240, and so on, it is a perfect straight line. And here is where we get the term linear growth. It grows at a constant rate, so it grows the same amount every term. Okay, so let's take a look at some formulas. We're going to have 2 formulas, and it hinges on this kind of setup piece right here. He says if a quantity starts at size P naught, now I don't have, I'm going to put the P naught in there, a little 0, and grows by D every time period, then the quantity after N times periods can be determined by using either one of these relations. Okay, now in terms of the problem we just did, right, if a quantity starts at size P naught, that would be our 8,000, right? That was our P naught in the problem. And grows by D every time. Well, every time it grew by 120, right? 120 tons. Then the quantity after N time periods, now what we just did is we made N be 60 in our previous example. Then, but you can use these general formulas. Okay, the recursive formula would say like, okay, P sub N means that the amount at any time. As you take P sub N minus 1, that's the previous, because N minus 1 is one less time period, plus 120. So let me give you an example of what I mean. If you want the amount of trash in the dump at the 60th month, which is what we wanted, then you would take the previous month, that would be P sub 59, and you would add 120 more. Now, the problem with the recursive form is to know the 60th term, you had to first know the 59th term. But if we had know the 59th term, we'd have to know the 58th term and so on. So it would mean I would have to work my way up there. It's not as handy for finding a term way out in the future, but it is nice to understand. Now, the explicit form is a much handier way to figure out something way out in the future. To find the 60th term, right, you just start with P naught. P naught is the 8,000 in the problem, plus D times N. Now, D again is the amount of growth each time. So that would be 120 in this problem that we did before, times N, the number of time periods, 60. You can see that that is precisely what we did above, right? So it's the same formula. But those are formulas you can write down in your notes to use later, and we'll use them in later videos. Okay, let's take a look at one last problem to see how this can work. We're just going to give a little recursive and explicit formula for this problem. A nuclear power plant produces 12 pounds of radioactive waste every month. Because you might think like, okay, which letter is that? Well, that's the change, right? That's the D. So D is 12, right? The radioactive waste must be stored in a special storage tank. On January 1st, 2000, there were 25 pounds of radioactive waste in the tank. Okay, that's how much we already had, right? That's P naught. That's what we started with. We started with 25 pounds of waste. And then it says, let P sub N represent the amount of radioactive waste in pounds in the storage tank after N months, right? Because we're getting some amount every month. So A, give a recursive formula for Pn. Well, recursively, the way that we find any term, right, is we take the previous term, which is written as Pn minus 1, and we just add the amount that it changes each time, in this case, 12. That's the recursive formula. Okay, that's A. And it's pretty easy to do, right? 25 plus 12 plus 12 plus 12 plus 12 and so on. But if you want to find one out in the future, then you want the explicit formula, okay? Let's write that as well. So the explicit formula would be, and you can get the equation from above, like you make sure you copy that down. P sub n equals P naught plus Dn. I'll go ahead and write that down so you can see how I'm using it. So it's P sub naught, which is the starting value, plus D times N. So in this particular problem, we would say like our P naught, we start with 25 pounds of waste. And each time it changes by 12, and N would be the period of time. Now, notice here, I'm just writing the formula. I'm not actually plugging in a specific amount of time. You're going to see us play these out a little bit more as we go through the next several videos, but I hope this at least lets you see the difference between recursive and explicit equations for growth.